All right, oops. Thank you so much, everyone, for coming to this talk. Let's see if this works. Perfect. Um, I have a lot of fond memories of being here at UW. In fact, I actually think that being here at UW really kickstarted my career in model reduction. So I was a humble engineer when I first started here, and I feel like I left a mathematician. So now I get to do a lot of research in math and applied mathematics and computational stuff. So, I'm really, grateful for the time here. So thanks everyone for having me. Um, so today I'll be talking about reducer modeling in a light that's not really, ubiquitous in model reduction. So if I were to say, how many of you know about meshless reducer modeling? What about meshless methods, numerical methods, meshless numerical methods? Cool. So not everybody, but then I say, how many of you guys know about finite elements? Right? Okay, cool. So I've been working a lot with meshless, methods. Basically, I did my PhD on meshless methods. So there's room for meshless numerical methods, especially for specific kinds of problems that are very beneficial, to cast them in meshless settings. So throughout this talk, I'll be talking about what meshless methods are, the problems that motivate the development of meshless methods, and where we can use them, and what motivates the development of reducer or modeling for meshless methods. So Steve and I actually just got this really cool project from the DoD Basic Research Office. So it's the acronym for the Basic Research Office is, of course, BRO. So we all know what a tech bro is, but do we know what a DoD bro is? So that's what I like to say. Anytime I start a presentation that's funded by that project, I like to say, I like to thank the DoD bro for funding this work. So, all right. So today's talk is going to be enabling model reduction of meshless non-local methods via model reference spaces. All right. So I'm going to start talking about the problems that motivate the work that we're doing, which is, at the lab that I work at, the Naval Research Lab, we're interested in a lot of problems that have to do with large deforming flows, with multi-phase interfaces or free surfaces. So think about, a flow past a cylinder, which I'm sure we've all worked on, but near the free surface. So problems like that. Okay. If you worked with compressible flow codes before, you probably know this benchmark problem, which is the triple point contact problem. You have three different fluids, all varying densities, high density ratios if you want. And basically, they're all traveling at hypersonic speeds, and you get a lot of discontinuities in this flow. So this paper is out of Lawrence Livermore National Labs, and basically that paper was highlighting how meshless methods are capable of inherently developing or inherently including a lot of discontinuities and different types of just flows that some mesh-based methods like finite volumes or finite elements might have to add additional bells and whistles to actually model this kind of a flow. So this is just an example, and I'll describe what meshless methods are. The top row here is a meshless method, and the bottom here is a grid-based method. So this is one type of problem that we're interested at the lab. Another problem is additive manufacturing, or aka 3D printing. So this is what you're seeing. What you're seeing here is basically a metal powder. So you kind of distribute metal powder on top of the substrate that you're seeing here at the bottom. And then you pass a laser through the surface and you melt the powder, creating a new layer of basically, I don't know, a thin layer of metal. And so what the simulation that you're seeing here is doing is it's passing this laser through, and this is a simulation out of a university out in Germany. But this is a beautiful simulation. There's lots of physics involved. I actually have a colleague of mine who says additive manufacturing is not multi-physics, it's all the physics because it includes everything from microstructure, development to, Marangoni effects, to cavitation, to porosity and things of that nature. This is a very difficult problem to model. But meshless methods offer the flexibility to model this very inherently in the numerical framework. So it's actually, I don't want to say quite simple because then I'd probably, get a lot of haters out there. But it's somewhat inherent in developing the physics into and baking the physics into this numerical framework. Now, this numerical framework is the SPH method for short. It's smooth particle hydrodynamics, SPH for short. And I'll talk a little bit more about that in a couple of slides. And in fact, we actually have an in-house code that we're developing at the lab. I'm the lead developer on what's called multi-physics. It's a play on SPH. But this is, we're trying to bake in thermomechanical, thermoelastoplasticity and things of that nature into our in-house code. So there's lots of work that we're doing with SPH for different multi-physics problems. One problem that really encompasses the benefits of meshless reducer or meshless simulations is this problem out of Lawrence Livermore National Labs. It's a beautiful simulation. This is basically a meteor entering the atmosphere. And normally when you're modeling these type of problems, you might want to couple, for example, the structure, you might want to cast the structure, or in this case, the meteor, in a different type of numerical framework than the actual fluid. But in this case, it's the same type of numerical framework. It's actually the SPH method for both the fluid and the structure. So this again highlights the flexibility that meshless methods have when we're trying to model very complicated physics and physical phenomena. So, I've kind of touched upon some of the benefits of meshless methods. Obviously, one of the biggest meshless benefits is that there's no mesh required. And you might be asking, why is not having a mesh beneficial? Well, from a mathematical perspective, maybe it's not that beneficial, but from an engineering and practitioner perspective, it is. Because a lot of the times what you have to do in practice is basically develop a CAD geometry, export that CAD geometry into a finite element mesh, which has to be certified, robust, and things of that nature, depending on what problem you're looking at. And then you run your numerical framework. But for meshless methods, you can actually operate in point clouds. So you can extract the CAD geometry, basically extract the points in your CAD, and immediately just start doing your numerical framework. And so that's obviously a big benefit, especially in practice. Another benefit, which I actually touched upon in the last slide, was that SPH and other meshless methods have a natural formulation when it comes to modeling multi-phase problems. And you can actually see an example of a multi-phase flow past a cylinder here. The air is at the top and the water is at the bottom. And then you can see the interface here. Obviously the interface is the differences between the two fluids. There was no additional framework. There's nothing else that you have to include or another coupling scheme or something like that to implement into the meshless framework to actually allow the simulation to run. In fact, this is the same actual equation. You just have to add a couple of, physical constraints to actually model the interface between these two densities of fluid. Now, I actually touched upon no mesh requirements to model very complex geometries. So here, for example, say you have a CAD geometry of a rotor. All you have to do is extract the point clouds from the CAD geometry and run a simulation inside of the fluid. So if you think about this propeller using traditional mesh-based techniques, you have to think about, okay, so how are my fluid domain and my structural domain going to communicate, and the interfaces between all these grids, how are they going to communicate? Versus in this simulation, you just have to cast everything into point clouds, and the boundary conditions are kind of taking care of themselves. So I don't mean to oversimplify meshless methods, because there's lots of work to be done to improve the fidelity of meshless methods, but it does offer a lot of flexibility in modeling very complicated simulations. So obviously there's never a free lunch. So there are several limitations to meshless non-local methods, but the one that actually funds me is the poor computational expense of meshless methods that stem from dense numerical stencils. So what does that mean? Basically, if you want to achieve specific levels of accuracy, you have to have a very dense numerical domain. So you need a lot of interpolation points. So this expense has really limited the use of meshless methods in time-critical multi-query problems like optimization techniques, uncertainty quantification, control, things of that nature. So the question that Steve and I are trying to answer is, can we overcome the expense of these meshless methods with reduced error modeling, right? And so I'm not going to bore you with how reduced error modeling actually works in practice, but basically what we're trying to achieve at the lab is, say, for example, we're trying to do some sort of multi-query task or time-critical application. Say, for example, we're trying to optimize a propeller or the design of a propeller. We're trying to run a simulation, query the quantities of interest and see if we're, essentially getting an optimal output in the performance or whatever that may be, right? But the red balloon here actually takes forever to run because it's, requires lots of, numerical points and requires a dense numerical stencil. So can we replace this with an effective surrogate model, which essentially in this case is a reduced error model? So that's what we're trying to do here, right? Okay, so has anyone ever worked with the smooth particle hydrodynamics method? No? Okay, cool. So the smooth particle hydrodynamics method, I'm just going to be calling it SPH from now on, really exemplifies a lot of meshless methods. So if you understand SPH, you can probably understand 99% of the other meshless methods around. Have you guys heard of Perry dynamics? Okay, one person, wow. All right. So this is really neat for you guys. This is good. Right, so I'm going to be going over the theory of how meshless methods work, and this is kind of probably the most important slide for the rest of the talk, because it really lays a foundation of how we construct the reduced error model in a meshless sense. So we're going to go ahead and start by introducing an arbitrary continuum, And this arbitrary continuum has a field quantity f of x. And think of this gradient, this blue color gradient as the actual field function, okay? And so the domain that we're looking at is omega. So we can represent that field quantity f of x as a convolution, right? And here the Dirac delta function takes in an argument that's very similar to almost a linearization about x. So think about, kind of like your surrounding neighborhood, and x is a point that you're kind of, trying to figure out the Dirac delta function. When we're doing approximation theory or we're trying to discretize the Navier-Stokes equation, we obviously have to do calculus on the approximations that we're doing, but I don't think anyone has ever done calculus on a Dirac delta function because you really can't, right? It's discontinuous. So what we can do is actually replace a Dirac delta function with a continuous argument or a continuous function, where if we define x to be the argument of the Dirac delta function, and we enforce the kernel to be somewhat continuous, either C2, C3, even C infinity continuous, so that as h approaches 0, we actually do recover the Dirac delta function. So now we're in business. Now we can do things like calculus and things of that nature. All right. So here we can actually approximate the gradient of this field function as you're seeing here. So this integral is still continuous in the domain. So we have to communicate that function, obviously, to the computer and actually discretize it in space. So what we can do is, normally in this stage, we actually introduce finite elements or something like that, or finite volumes. But in this case, I'm actually going to introduce material points. In this case, I like to call them chunks, but SPH stands for particles, right? So these are actual particles. So don't think of them as like actual physical quantities. These are just numerical quantities. These are chunks of masses that are moving around. And so instead of actually having d omega, we have a volume, right? And then if you look at the summation now, so we replace the integral with the Riemann sum. This now is starting to look like somewhat of an interpolation function, where the weights are basically f of x multiplied by the volume, and then w is your interpolation function. And so this is how we can actually discretize our Navier-Stokes equation if we substitute that into the actual Navier-Stokes equation, right? So the way the interpolation works is that each of these neighboring particles of, say, for example, particle I equals 9, all the neighboring particles in this continuum are actually telling this particle what to do through interpolation, right? And the interesting part about this, discretized continuum is that none of these particles are tied to the neighboring particles throughout the simulation. These particles are free to move in space throughout the simulation. And so this is the difference between a mesh-based method and a meshless method. There is no connectivity that's fixed throughout time or space. So now that we have a discrete form of the SPH approximation, we can substitute that into the Navier-Stokes equation. And if you're interested more in talking about SPH as a numerical method, we can talk offline. But this is a good reference to get started. SPH, where I'm using for the rest of the talk, I'm going to be using delta plus SPH, which is a variation of SPH. There's lots of bells and whistles to improve the fidelity of it, and this is one of them. So this is super important slide. So feel free to ask me any questions if there are any. If not, then I'll just keep moving forward. Oh yeah.
What is the difference to a Lattice-Boltzmann method?
Right, good question. So the Lattice-Boltzmann method, and I'm actually going to touch upon that. You've kind of done a spoiler here, but the Lattice-Boltzmann method requires a background grid. Right. This is probably one of the few purely meshless method. There's no grid in this, so there's no background grid involved.
But the right-hand side of the Boltzmann is more or less the same way as the meshless method.
Correct. Correct. Yeah. So yeah, exactly. So there's no background grid with SPH, and there are some different probably numerical formulations or different types of discretization involved in the approximation that you're making with Lattice-Boltzmann. But more or less, the Lattice-Boltzmann method is very similar to the material point method, very similar to some of these methods like point and cell method that require kind of a background grid. SPH doesn't require that. Good question. Okay, so hopefully that wasn't too boring, because I'm gonna bore you even more now with things that we've all seen. If you read Steve's book, we've probably seen this slide already that I'm about to introduce. So I'm going to be talking about the wonderful Galerkin POD projection for linear cases. But I'm doing that just because I want to introduce the notation that I'll be using for the meshless reducer remodeling component. So hopefully you guys stick around for this. All right, so let's go ahead and get started with kind of this formulation here. So in reduced order modeling, we have an ODE that we're interested in, where X can be your state space. In this case, it'll be your SPH state, right? So in that case, it'll be your density, momentum, and temperature or energy. And F is your Navier-Stokes functional, discretized in SPH form or finite volume form, whatever. So in reduced order modeling, we seek an approximate solution to this ODE in an affine trial space. So we're essentially, what I like to call, what we're doing is data-driven separation of variables. So we essentially try to find a basis function phi that we can get from data, and then we're projecting the actual approximate state space onto that low-dimensional manifold, where X hat are the low-dimensional coordinate system. So to build the affine trial space for the basis function that we're looking at, the data-driven basis function, we go ahead and sample a parametric space of interest. In this case, we're using, for example, a two-dimensional parametric space where the density of the gas is one parameter and the density of the fluid is the other. So we can go ahead and run a simulation. And this is the simulation that I showed you earlier. And so that'll be, one training sample, and then we can continue running that across different variations in the parametric space. And we create a snapshot tensor where we can do things like the proper orthogonal decomposition and extract the basis function that we want. In this case, I'm talking about Galerkin POD projection. So we're going to assume that we're doing the singular value decomposition or method of snapshots to extract this basis function. And so because we're using a POD approach, we know that the basis lies in the Stifel manifold, which is essentially the space containing all orthogonal functions. And because it's orthogonal, we can do the thing that we like to do the most, which is do a Galerkin projection. And now we have a really nice, simple, reduced order model where the dynamics evolve in a low dimensional state. All right. So this is, of course, for linear functions. But for nonlinear functions, we get a little bit more complicated. So I'm going to go ahead and start talking about some of the different variations there are in reduced order modeling with nonlinear reduced order models. So here we're trying to approximate the ODE and say that F is a nonlinear function. The way you would normally do it with a Galerkin projection, of course, is the projection of the dynamics onto low dimensional subspace can actually be shown to be to provide continuous optimality in the L2 norm, the full order model residual. So this is kind of akin to optimizing and then discretizing in time. But another approach is actually a Petrov-Galerkin approach. Specifically, we've been working with the least squares Petrov-Galerkin approach, where we kind of flip the Galerkin approach on its head, and we discretize in time first, and then we optimize, right? But the thing about doing this type of reduced order model is that, of course, when F is nonlinear, it's not always guaranteed that you're going to project onto a low dimensional state, or the resulting operations will result in something small that you can compute on, right? And so what normally you end up doing is you try to do what's called interpolation of the nonlinear terms or perform hyperreduction, which, if you've heard of DIME, U-DIME, Q-DIME, all these different variations, those are all, something called hyperreduction. That's a coined term, a term that was coined at Stanford and Charles Group. There are different flavors of hyperreduction. Like I mentioned, ECSW is another one. And we've actually, Steve and I wrote a paper in 2022 on a different type of hyperreduction approach for n-body problems called the projection tree reduced order modeling technique. And there's also empirical quadrature. So far, all this is available in literature. You can see all this. This is nothing new. This is just kind of regurgitating some of the stuff that's out in the literature. I just wanted to kind of build some foundation up for you guys so you can see how we're implementing some of these approaches in meshless model reduction. So we've actually tested LSPG, which is the nonlinear reduced order modeling method that I just showed you guys, on smooth particle hydrodynamics for a nonlinear heat equation to kind of represent a very simple additive manufacturing simulation. So this is actually part of a report that I published with the Naval Research Lab. I like to call the pseudo postdoc that I had because I was on a fellowship, but I wasn't an actual full-blown official full-time employee yet. But if you're interested more on this research, it's publicly available. You can just look me up on Google Scholar and you'll find it. So what you're going to see here is a simulation of a laser passing through the surface, which is supposed to emulate kind of, the melting of a substrate. All right. So here you see that laser passing through the surface, and we performed hyperreduction on that, on this simulation here. And basically, hyperreduction is kind of a quadrature rule where you don't have to integrate everything in the domain. You can just choose a couple of points to actually achieve the same results as you're seeing in the full order model simulation. So the full order model actually had close to 400,000 particles. The reduced order model had 9,000 particles, and we got about 200x in CPU savings, and the quantity of interest error with respect to the full order model was less than 1%. So this is really nice. It was pretty good results, and you can see these results on the report that I was talking about. If you guys are familiar with the Kolmogorov N-width, then you know that this is an advection-dominated problem because we're literally advecting a laser through the surface. So one thing that I didn't include here that I should have is actually the dimensions of the bases that we're using are quite large. They're up to like 500, 400, dimensions. So, when you're talking about doing linear system solves with dense matrices, that can get quite expensive, right? And so even though our memory footprint is quite small, the wall time is not as fast as we would like it to be. And so to improve the Kolmogorov N-width, there's an approach called the local reduced order basis technique, where essentially you're discretizing your parametric space. And you can essentially build many bases depending on where you are in the parametric space. And so what you end up developing is an adaptive reduced order model, which is what you're seeing here, where the hyperreduction can also be adaptive. So you're jumping bases in the parametric space depending on where you are in that parametric space. So we applied this to an inverse problem. We got decent results. There are some improvements that we have to make because, as you can see, we only got a speed up of a factor of 6. And the CPU savings, I believe, were about 26 or so. And this is really just, there are other improvements in numerical, techniques that we have to kind of improve to actually get this to have better results with the CPU savings and the wall time savings. Also, this is relatively a small domain compared to this problem. So the point is that, a local reduced order basis approach could work for these types of meshless simulations. So far, I've introduced nothing new. All this is out in the literature. So I don't know if you guys caught this, but there's a key word in this slide that I kind of just glossed over, which was works well with fixed SPH domain and pre-computed gradients. But in fluid flows, right, when there are kinematics involved, these particles have to move. If you notice, these particles have been staying stationary. So the main question that we have to ask is, can we use these state-of-the-art methods in reduced order modeling for a general framework of meshless non-local models? The answer is no, or sometimes, or maybe. So I'm going to show why traditional reduced order modeling methods don't really work when we're talking about meshless methods where the particles or the numerical points actually are free to move in space. So I'm going to introduce this Rayleigh-Bernard instability, which is a natural convection fluid dynamic phenomenon in thermal fluids. It's beautiful simulation. And essentially what we're doing is we're heating this fluid, which is in green, with this hot boundary condition and this cold boundary condition. I'll go ahead and play this in a couple seconds here, but I want to hit on the point that the fundamental reduced order modeling approximation that allows all these methods to work that are state-of-the-art in reduced order modeling assumes that each of the numerical points are fixed in space to draw out these low-dimensional features at specific locations in the domain. So in short, basically, these nodes will stay at fixed points and gather information about features at specific points in space. So if we focus on this specific region here, this region, and this is temperature, this is the temperature field, by the way, this region is going to get good at understanding what the low-dimensional features are at that location. So if you think about the singular validity composition, right, which is, basically kind of like the eigenvectors, the correlation matrix, I believe, it's going to get good at figuring out what the shapes at that location are, right? That's not how meshless methods work. So meshless methods allow numerical points to move in space and do not bind these numerical points or initial neighbors to specific features in space. So basically, these particles, the particle I, for example, will gather information about locations it visits. So if you look at the simulation, which is an SPH simulation, you look at these numerical points that started here next to each other, they do not end up at the same location at the end of the simulation. So if you're actually going to cast a snapshot tensor, could you imagine what these modes will look like if you're trying to figure out the correlations of these two different, particles in the domain? You're going to get like noise, static. And in fact, I'll show you guys a couple of modes that are kind of fun to look at in a couple slides. So to kind of hit further on this point, I'm going to introduce numerical stencils and adjacency matrices. But first, let me set up what you would call the naive dimensionality reduction of unstructured data, which SPH can be thought of as unstructured data. Okay. So if we think about each of the particles in SPH as interpolation points, so I'm going to call them particles, and we look at their state vector, that includes density and momentum, or in this case, velocity and velocity in the X and Y direction. So X is essentially the state vector of particle I at time step n. We can go ahead and create this naive snapshot tensor that you normally would for finite elements, finite volumes, or your traditional Galerkin projection technique, right? And you concatenate the state vectors depending on the particle, and then you basically align every time step in this matrix. So you do your reduction, and this works really well when this numerical stencil is fixed in space, time, and connectivity. So here I'm going to introduce this numerical construct called the numerical stencil. And so how many of you guys are familiar with the adjacency matrix? Oh, perfect. All right, cool. So I don't have to explain it too much. All right. So basically, say, for example, we look at the numerical stencil, the node number 5. This could be your SPH numerical stencil or a finite difference or volume stencil. It doesn't really matter. But, we're going to add ones to each of the rows that, the index number 5 is connected to. Okay. So traditionally, when we're looking at finite elements, finite volumes, and all these mesh-based methods, you're going to have beautiful banded structures in your adjacency matrix. And that's how this structure looks like for the rest of the simulation, if you're not doing anything like, adaptive mesh refinement or anything like that. Something else that I want to highlight before I actually start running these animations, this that you're seeing down here is the particle ID distribution. So think of that as I'm like labeling each particle in the SPH simulation with a number. And so blue essentially is like particles 0 through 500, and red are like 3,500 through 4,000. All right, so I'm going to run this simulation or this animation. And so this is the equivalent dynamic adjacency matrix of this simulation that you're seeing here. So this is the same simulation that I showed a couple slides ago. Anyone want to guess what the SVD looks like of this? It looks like TV static, right? So how can you extract low dimensionality from an adjacency matrix that looks like this? And this is, my man here just spoiled everything for me, but we're going to introduce a reference grid. So we're going to introduce a reference grid where we can essentially interpolate some of the SPH data onto a fixed reference space and then extract low dimensionality from that reference space so that we can go back to meshless space with low dimensionality in mind. So these points here are not finite elements. These are not any of the mesh-based techniques that you know about. These are just interpolation points that we're going to use, okay? But we can, this domain can be arbitrary. But what we can do is actually introduce the data points as the SPH simulation, where essentially what we're doing is the black points are the interpolation points and the red points are the SPH simulation. So this black point, anything that falls inside of this radius, 2h being some sort of radius coefficient, anything that falls inside of this radius gets interpolated onto this black point. Okay, so in mathematical terms, what that looks like is if we have this function, arbitrary function f of x, the black variables are going to be the reference interpolation points and the SPH data is in red. We could basically do interpolation of the densities of the SPH simulation and the densities, the momentum, and the temperatures on this interpolation grid, which is a reference point. And then we can start doing things that we normally would in traditional research modeling, which is discover low dimensionality with an autoencoder, SVD, whatever you want. All right. So surprise, surprise, that simulation that I showed you guys earlier today was actually SPH data mapped onto a fixed grid. So this is actually SPH data that you're seeing here, but it's been interpolated onto a fixed grid. So then we can get beautiful modes, right, that we all know and love on this grid. But check out the meshless mode, right? Does that look low dimensional to you at all? Probably not, right? It almost looks like TV static. What was more interesting though is when we started plotting the singular valley decay of these simulations. So what's interesting to note is that there's a discrepancy in how much energy or how many modes you need to recover the same amount of energy. So in the mesh-based approach, you only need 22, or sorry, in the reference space, you only need more or less 22 modes to recover 99.99% of the energy. While in the meshless data, you need about 68 modes to recover the same energy. And this is really interesting because there is no advection here whatsoever, but we're seeing the same issues that you would in advection-dominated problems. And you're seeing issues with the Kolmogorov N-width when it comes to the mixing, fluid dynamics that you're seeing here. So this is really interesting, and honestly, this problem and kind of working on this reducer modeling really opened up a can of worms that I want to do all the analysis. I want to do all the math, and when it comes to this type of research. But if anyone's interested, let me know and trying to figure out, why this is. So now that we have a way to extract low dimensionality from meshless data, should we go back to meshless space? If so, how? So this is my opinion, right? It does not reflect the opinions of the Naval Research Lab. I'm just kidding. So yes, we should go back to meshless space. I think so, because then why are we doing all this, right? The reason why we need to go back to meshless space is because we're trying to essentially take advantage of the meshless benefits of modeling very complex simulations, like what I showed earlier in the first slide. So, and the other reason why we should go back to meshless space is, well, then how do we do reducer modeling in reference space? Can't really, because then you're talking about almost a data assimilation method, right? If you're going to use the reference grid to use some sort of finite element formulation, then your mesh has to align exactly to the reference space that you're using, and it gets messy. So yeah, we should go back to meshless space, in my opinion. So if so, how do we go back to meshless space? So this was actually taken out of Steve's data-driven book. It's actually a really good chapter on continuous formulations of the POD. It's really nice. So what I'm going to do is try to think about the POD as a least squares problem, right? Where X is essentially a vector. It could even be a snapshot tensor, where of dimension n. So think of these as measurements of some sort of data. If we drive n to infinity, in fact, the modes that come out of this least squares problem, we can treat those modes as functions of space. And so if we treat them as functions of space, we can use this function of space to essentially map back to meshless space. In other words, we can insert the particle position into this POD function, and it'll output the modal quantities in the low dimensional state. And so we can but obviously we can't drive the measurements to infinity. So what we're going to do is construct a continuous approximation of the POD modes using scattered data interpolation. So instead of actually, we can perform this POD formulation, get the modes, right? But then we're going to have to approximate these modes with some sort of interpolation in space. And so we're doing that interpolation with polyharmonic splines. I'm not going to get into too much of the details here, but essentially we have to pre-compute the weights, where R is a position of the particle that we're looking at, C is a position of the reference space modal quantities, and V are just basically polynomial regularization terms in the polyharmonic splines. So now we have the POD modes as essentially pseudo functions of space. And so now that we can represent a meshless or a pseudo meshless POD mode, what we can do is start casting everything into the POD Galerkin approximation, or the reducer modeling approach. So this is why I actually kind of went over the ingredients list of Galerkin reducer modeling earlier, because I wanted to show you that, of course, we're going to start constructing the formulation here. So we seek an approximate solution of the ODE, right, where X is approximating, or X tilde approximates X. But instead of the original phi, which comes out of this, POD least squares problem, we're actually going to use the interpolated phi, which is phi tilde. Now we can start playing games as far as substituting that into the SPH equations, or the approximation. But one thing that came out of this was actually very interesting, is that because this is an interpolation of the original modes and not the actual modes themselves, this does not necessarily, orthogonality is not necessarily enforced when it comes to the interpolation. So this is actually another interesting problem that, we can probably talk offline on how to enforce orthogonality of the interpolation points without using machine learning. I feel like you can do that with machine learning. But yeah, so orthogonality is more of a convenience in this Galerkin projection, not necessarily a requirement. It just provides a basis where you can take the transpose of the matrix instead of, the pseudo inverse, if you want. So it wasn't really a big deal that orthogonality was not guaranteed, but we took the pseudo inverse of this phi tilde matrix, and now we're talking about a meshless Galerkin reducer modeling approximation. So I mentioned earlier, when we were doing nonlinear reducer modeling, you're going to have to back project to actually get, the full nonlinear functionals. So in this case, not only do we have to do that with this phi pseudo inverse times f, but we also have to project back the velocity so we can advect and push the particles in space to the next position in the time step. So obviously this is going to scale poorly, but the purpose of this work was to see if we can find a meshless way to project, low dimensionality onto some sort of meshless framework. And so, of course, doing hyper reduction and things of that nature are going to be part of the next chapter of this project. So, we're excited about the opportunities to work on this very difficult problem. Okay, so now I get to show you some results. So we tested this. On a lid-driven cavity, right? So this is just the SPH simulation setup. This is the magnitude of the velocities. This is the full order model, by the way. And then these are the particle ID distributions that I showed earlier. So here we're gonna Great. Here we're gonna run the simulation, and what you're gonna see here is the evolution of the velocity field, and here are the particle distributions. So I'm just gonna let this run so you guys can really be amazed by the simulation. So the particle distribution is really interesting, and it actually does play a role in the next slide. So this almost looks like a really nice cinnamon roll. So just pay attention to the pattern here, right? It ends up kind of swirling on itself. So here are the preliminary results. Hope NRL is not mad at me because the emblem is just not there anymore. I don't know why. Okay, so here are the full order model results on the left, and here are the reduced error modeling results on the right. This is only 4 modes, but you can kind of see the silhouette of the actual, lid-driven cavity flow, which is really nice. One interesting thing that I actually realized last night looking at these results were, if you really pay attention to this feature here, there's kind of like a little whip at the end of this, feature, right? It's kind of nonlinear in that sense. But if you look at the feature in the same location in the reduced error model, it's almost just like a superposition. It doesn't really take into account like that little whip. And so if we look at the particle distribution as well, what you're going to end up seeing is that the full order model swirls on itself several more times than the reduced error model. So something is happening where the modes are kind of damping the actual velocities. So there are more swirls here than there are here. This is almost like the silhouette of the actual result. So it kind of works, but it kind of doesn't. But honestly, if it was 20 years ago, these results would be really, nicely cited, because Galerkin projection didn't really work back then either. So we're excited about these results because this is a new reduced error modeling technology in meshless methods. But to show you quantitative results and not just qualitative results, what I'm going to do is I'm going to plot the velocity field along the center line of the simulation. Same thing with the full order model. So I'm going to plot the velocity along this line down here. All right. So blue is a full order model. The other points are the actual reduced error models. What's really interesting to see about these results is that this is, by the way, the final time step. So the steady state solution, essentially, at the center line. What's interesting about these results is that you really only need one mode to approximate the steady state solution nicely. And so this is what you're seeing here. You see that blue mode and the blue line, and then you see the red line. That's the first mode only. But everything before the steady state looks like garbage, because you can't really capture the dynamics of the actual simulation with just one mode. But then you start including 2 modes, 3 modes, 4 modes, and then all of a sudden the simulation starts damping itself. And so you might be asking, did you try 15 modes? Did you try 100 modes? The answer is yes, but for some reason, the results were incredibly unstable. And so Sam Otto and I might have a paper coming up where we actually try to figure out how to explain that. And it probably has to do with oblique projections to capture fast dynamics. So that was really interesting to talk to Sam. I'm glad I came to talk to him about that. So all in all, I'm pretty stoked about these results because reduced error modeling hasn't really been applied to meshless methods. And clearly, Galerkin projection is not the only way to go. There's different types of projection techniques that we can, look into to improve the results here. So, let's see how I'm doing on time. Cool. So that being said, let me just go ahead and start the summary. So we introduced a pseudo meshless approach, right? I'm calling it pseudo because we introduced that background grid to extract the POD modes. So that's kind of new that we kind of introduced in this presentation. And the approach retains the meshless benefits as a reducer or modeling dynamics evolve in a low dimensional state, but you can project back to the meshless state to retain the benefits of being meshless. And so the verification tests are good, are okay, you know, as good as you can expect, you know, Galerkin projection for nonlinear reducer remodeling. So we're just really excited about some of these results that we published or that we're publishing and hopefully, you know, putting up on the archive soon. As far as the outlook, like I mentioned, this really did open up a can of worms when it comes to reducer remodeling for meshless methods. There's so much analysis that needs to be done, error bounds quantification, just everything, literally almost from step one in reducer remodeling. So hopefully I've convinced you guys, motivated you guys to start looking at reducer remodeling from a meshless perspective so you guys can help me out, figure this stuff out. I'm going to leave it here, but just wanted to let you guys know that we have a paper underway that'll include other examples like Taylor-Green vortices, and we're going to include Rayleigh-Bernard instabilities and things of that nature. So that's underway. So thank you guys for having me.
All right, at this point, we would like to open the floor for questions that I'm going to try to balance between the in-person audience and online. If all members online have questions, please write in the chat and I will read it out. Yeah, happy to start with whoever.
Thanks.
Still new for the meshless stuff, so I'm trying to think in a sort of traditional finite element model where you're going to produce for modeling. I understand, you know, you might have n midpoints and m modes. So when you do the modeling, you go from n equations to m equations. I wasn't sure in meshless when you do this, is the original number of equations sort of like the number of particles, and you still end up with one equation per mode, or is it different?
So in finite elements, I guess it would be kind of like the number of nodes times the degrees of freedom, right? Yeah. Same thing with particles. It's going to be one particle times the number of degrees of freedom.
Okay.
Right. But then when you're doing the projection, it'll be just m. So it's not like m times the degrees of freedom, right?
So the saving is scales from like number of particles to number of modes.
Correct. Yeah.
Small questions. On page 7, you mentioned the ODE of the semi-discretization.
This one?
Yeah, you said ODE system, right? So the people use just ordinary method, classical method, like a Makuta method to solve that ODE.
Yeah, you can. But the thing about this least squares Petrov-Galerkin projection is that it only works, or it's only effective for implicit methods. So if you're going to do a Runge-Kutta, you know, is there an implicit Runge-Kutta? I feel like yeah, it should be okay, right? Yeah. But if you're using explicit methods, or if you drive the time step in this residual approximation or this residual, you're actually going to end up recovering the Galerkin projection.
Okay, so but can you use like a prediction correction method?
Yeah.
The principle.
Yeah, like a Hume's method or something like that.
Yeah. Also, now on next page, you mentioned nonlinear heat equations.
Yeah.
What do you mean?
Oh, thanks. I forgot to mention that. So the material properties are temperature dependent. So in that case, you know, the heat equation, obviously we're solving for the heat equation, and the material properties evolve nonlinear with respect to the temperature.
Okay.
So like density, the heat conductivity, the specific heat evolve nonlinearly with the temperature.
Okay. So we're talking about low dimensional PDEs here, right?
Yeah.
How about high dimensional PDEs? 3-dimensional or high?
Oh yeah, you can do that. I mean, this is a 3-dimensional P, right?
Okay.
Yeah.
Okay. So yeah. So meshless method basically is that you find the difference on the element method. We know that we have adaptive methods.
Yeah.
And anything like that in meshless, because you don't have mesh.
That is actually a new area that people are starting to look in, where like what's interesting is you're starting to split particles. So if there's an area of interest that needs a lot more, you know, refinement, you can split the particles into two using lots of techniques. And that's a really interesting approach. It's called, for SPH at least, it's called multi-resolution SPH.
Okay.
Yeah.
So last question. The title of your talk says non-local.
Yeah.
In which sense?
Non-local in the sense that you need a non-compact support. So a very large support when it comes to your neighboring interpolation points.
How about the spectral method?
Spectral methods, there are reducer remodeling techniques for spectral methods, but again, it's all on a grid. So the thing is, you know, spectral methods would work, and I feel like there's lots of literature with spectral methods.
Okay.
Yeah.
Okay, just small last one. A meshless method has been used for inverse problems.
Yep.
Any comments?
Has been used for inverse problems, like optimization problems?
Yeah, similar to that.
Yeah. We actually did use what you're seeing here. This was an inverse problem where essentially we didn't know the laser distribution or size. And so we kind of tried to do an Elder-Mead approach to kind of figure out what the radius was and the power of the laser. Yeah. So we're working on that paper right now.
Oh, okay, so far that's.
Yeah.
Thank you.
Yeah, sure.
I don't know much about these metrics methods, but I kind of I'm using this computation for approximating the gradient of F, and have you considered trying to do some sort of using kernel methods that basically interpolate your interpolation point and give you a mean and a variance associated with the uncertainty.
No, I haven't done that. That's actually kind of interesting. I haven't thought of that, to be honest. But I'm using what's called the C2 Wendland kernel, which is, fairly robust and widely used in SPH. But it's really interesting about what you just mentioned about the uncertain or the distribution quantities and things of that nature with kernel. But no, we haven't looked into that.
I remember what slide it was. In the perspective I'm coming from, the discrepancies.
Okay.
So you talked about the reconstruction of I don't remember exactly, but basically how you needed different numbers of nodes for reconstructing stimulated energy.
Right. This slide.
Yes. So that discrepancy between the like mesh reconstruction versus the meshless reconstruction.
Right.
Have you investigated if there's any like structure in the discrepancy between these two? Like at that line.
Yeah.
And if you like look at what those actual reconstructions are, and you kind of like.
Oh, interesting. I wish I would have put this really cool simulation of the reconstruction of SVD at those modes. It seriously looks like something out of a Marvel movie because it almost looks like a weird tesseract of the SVD modes. It's just like all jumbled. It doesn't make any sense when you're doing the SVD. I have the slides here, so if you want, I can show you after. Yeah.
So you mentioned also spline interpolations. Yeah. So
Is it maybe this one?
which page number? Yeah.
Polymer.
So anyway, so did you use like B spline or cubic spline, this kind of things? Or different?
We haven't tried. Yeah, we haven't tried the B splines or anything like that. We normally tried the polyharmonic splines because those are for unstructured data, for scattered data. And that's kind of what, SPH is, it's unstructured data. And so B splines, I'm not sure if you actually need to have an inherent structure to them.
Derivative and second derivative.
Right, yeah.
Pictures will be continuous.
But in this case, in this case, I don't think we're just trying to approximate the mode. So it's not like we're taking the derivatives of the modes or anything, but yeah, that's a good point. We could do B spline things of that nature.
Could you talk a little bit more about the construction of the reference grid?
Sure.
Like sensitivity, like you just go back to the.
Yes. Yeah, with Kenai.
Yeah, so how is this defined, like based on?
Right.
When you introduced the slide, this was like it seemed.
Yeah. So normally how I've been doing the simulation. So if the lid driven cavity flow problem uses the grid of the initial time step. So kind of how you're setting up your SPH simulation, you use the initial distribution of the particles as your grid. But what I actually found out is that if you use the relaxed version of your particle distribution, relaxed meaning that your particles have moved significantly enough and they find kind of their own equilibrium or whatever, it actually works a little bit better for the interpolation. So what I ended up using in some of the results that you're seeing here is I used the particle distribution and positions of the last time step as my grid. Yeah, or as my reference space.
Yeah. This strikes me as very similar to macrographs. On the arbitrary point defines
Right.
to shrink to the grid. So, and
having looked at graphs, they are very sensitive to like appropriate things of like cluster parameters and stuff.
Yeah.
But I'd be curious to.
Yeah, definitely. And that's, like I said, there's just so many different types of variations that we can do when it comes to this. It's like, this would probably be a dissertation, but I'm not really in the mood to do another PhD, to be honest.
Yeah, one last question is that
Sure.
we know that meshless specific methods, the theory depends on radio basis functions by Mark Power and Martin Billman. So any of this kind of related to convergence and stability analysis conservations based on your simulations.
I would love to do that. Yeah, definitely. There's lots of work, like I said, there's a lot of analysis that we have to do. This is almost like we got together one night and said, hey, maybe this will work. Let's give it a shot kind of deal. But yeah, if anyone really wants to work on the analysis with me, this would be great. Yeah, so definitely something that we'd want to do. Yeah.
Thank you.
Yeah.
These meshless methods, they work well with compressible flow fields
Yeah.
because like a lot of particles can bunch up at certain locations.
Right. Yeah. So that's a good point. And in fact, so with respect to compressible flows, SPH was actually developed initially for compressible flows. In fact, it was developed for astrophysics. So, you're dealing with really high Mach numbers and very compressible gases and things of that nature. But for incompressible flows, you're right that some of these points can kind of clump up. And what happens if, you have an inverse square law sometimes, like what happens if two particles are on top of each other? Do they kind of adhere? And so delta plus SPH kind of takes care of that by essentially adding a particle regularizer term that you're seeing down here, where it kind of destroys all sort of conservation by shifting the particles just a little bit so that you avoid all that.
And that adjacency matrix you construct later, like if you had a compressible flow where you're not adaptive, like everything would just be like if you're doing that, you're kind of having a radius and then you're checking if it's within that radius here.
Are you talking about like in the SPH? Here?
Yeah, there. Like, and then the way you're finding that stencil is because if everything falls in the same ball, then you're considering those points, right?
Right, exactly. Yeah.
Like, but if everything fell, if all the points in the flow field fell into a ball and nowhere else, like, would that be a problem?
Of course, I would ruin everything. But that's the but that's the SPH method. It actually doesn't do that. You can add, kind of these quantities to actually fix that. Yeah.
We have a couple of questions from online. Actually. One question was from June Zhang. I don't have any background in fluid. Why are simulations in 2D instead of 3D?
Hey me. No, I'm just kidding.
Yeah.
So basically we're just testing we're testing, methods. It's not really a production level code yet. So we're trying to test things on very simple codes and things of that nature. I actually did just get that same question from my boss earlier today. He said, hey, when are the simulations gonna be ready in 3D? So I told him soon. So yeah, but it's not like we're trying to avoid, doing 3D. Some of these applications definitely can be done in 3D as well.
Mm-hmm. Another question was, does the meshless reduced order model technique work for any system geometry other than rectangular grid-like space?
That's a good question. I haven't really tested it out yet. I suspect yes. I'm going to be testing this out on several different problems. And like I mentioned, we just opened up a can of worms. So literally these results are about a week and a half fresh. So yeah. So basically I did commit to making this presentation before I had the results.
Got it. Okay, I think that's everything we had from online. So let's thank Stephen again. And for our guests from online, please look at our information channels to know about the next seminars coming up. And thanks for coming, and see you again. There's many people uploading.